Today's topic, resolution, is, you've seen this word a lot before. You see it to describe screens, right? Screen resolution. Normally, a better resolution means you can see more details, right? In this case, the resolution is the ability to differentiate between two objects. Right? We have object 1 and object 2. If you're able to tell the difference between these two objects, you say these are resolvable. If they look blurry and you cannot tell the difference, right, they're not resolvable. So if you have better resolution, you're able to see smaller differences, right? So higher resolution has a smaller minimum angle, theta. We can tell the difference, right? So how is this related to waves though? And the thing about this is there's a criterion, right? And we will make this a simple system. Let's make this monochromatic with one wavelength. And there's a two source, right? So there's two lights. Normally, if they're really far apart, you can see there's two different lights, right? And you can differentiate them. And when they go into your eyes, they make this single slit diffraction pattern inside your retina, right? So because of this object 1, inside of your retina, you see this red pattern. For the object 2, you see this blue pattern. The maximums are in different places. So you see two different lights. But they come closer and closer together, right? At some point, you will not be able to tell the difference anymore, right? And the question is, what is that point where you cannot tell the difference between two lights, right? And we call this the Rydell criteria, right? The criteria is the minimum angle where you can still tell them apart. And below that angle, you cannot tell them apart. So before we see this in a graph, let's define this criteria as the minimum angle, right, is going to coincide with what we call the first minimum. So it's the first minimum for single slit diffraction. Right. So in the terms of the red, it's from here to here. So if the second peak, which is here, second peak is here, right? If this is farther away than this first minimum, you can tell the difference. If it's closer, you cannot tell the difference anymore. And I prepared a demonstration of why this is. So first, let's get rid of this. So there's the two peaks, right? The first diffractions. I just drew them until the first minimum. I didn't draw anything past the first minimum, right? So let's see, I can move them around, right? Can you see this? To whatever distance I would like them to be. And when you see them inside your eyes, what's going to happen is, actually let's make this range slightly larger. So when you see this in your eyes, what you're going to see is the sum of the intensities. That's what the cells inside of your eyeballs see. So your eyeballs will just see two peaks. And it's two different points of light. Right? Let's see what happens when they come closer together. You keep coming closer together. Keep coming closer. And there's a point where they do this. And it's completely flat. Right? At this point, you can no longer tell that this is 2 points, right? It can be just one big light. There is no dip to tell you that they're different. And this is going to be the minimum distance, right, between these two. If I draw them again, you can see that this minimum distance, where you cannot tell, is the borderline where you can tell them apart or not, is going to be distance to the first minimum. Right? If you get closer than this, let's try this out. All you see is this green line. This is all you see. You cannot tell that there's two lights. You only see one bright light, like this. And as they get closer, even closer together, you see one big light. And here, they're almost in the same place. Right? So in your eyes, you only see this green line. You cannot tell the difference, right? And this is the right criteria. If you try to go further away, let's say here, slightly further than the single slit, or the minimum, right? So the minimum was here. This is slightly further. If I turn off the other ones, you can see that there's a slight dip. Right? So what you guys see is there's one bright point here, a small reduction in the brightness, and then another bright point here. So you can still kind of tell there's two, not just one. Right? So it's very important to be able to calculate the first minimum for a single slit. Right? Remember, these are still slits. These are not holes, they are slits, right? Vertical. And this first minimum, we calculate to be the wavelength divided by the slit width. Right? This used to be sine theta, right? For the minimum. An approximation says sine theta is equal to theta. So this is the first minimum, right? Closer than this, you'll not tell the difference. Farther apart than this, you will be able to tell the difference. One interesting thing is, you can improve your resolution by making the wavelength smaller. If you make the wavelength smaller, the minimum becomes smaller, and you can look at smaller details. If you make the slit size bigger, right, you can also have the same result. A bigger receptor, bigger hole, right, makes the minimum angle smaller. Also lets you see smaller details. But this only applies for slits. So these are holes that are like so, right?